Assalamualaikum. We are from Group 2. Today, we will present about data-driven source control, optimizing data center energy efficiency and thermal stability. I will introduce my team members. First is Kairina Fahira. Second is me, Nur Maslina. Third is Nur Aisha Umaira. And lastly, Nur Yasmin Hani. The rapid growth of AI and cloud computing has increased the heat generated in data centers, leading to higher cooling energy demand. Conventional cooling systems use fixed settings that cannot adapt to changes in server workload and ambient temperature, resulting in unnecessary energy consumption. This project proposed an IoT-based data-driven code source control system to monitor temperature and cooling power consumption in real time, improving cooling efficiency and reducing energy use. The problem here is data centers use a lot of electricity because cooling system must run all the time to remove heat from server. Many cooling systems are use fixed system that cannot adjust to changes in server workload and surrounding temperature. This causes more energy to be used and make cooling less efficient. So, the objective of this system is to monitor the initial temperature, outlet temperature, ambient temperature, and cooling unit power consumption in real time using IoT based monitoring. Second, to improve thermal stability and energy efficiency in the data center. Lastly, to optimize the operation of the cooling system using data driven control. Next is system specification. First, initial temperature to measure the temperature entering the cooling system to determine the cooling load. Second, outlet temperature to measure the temperature leaving the cooling system to evaluate cooling performance and thermal stability. Third, ambient temperature to measure the surrounding temperature because it affects cooling demand and cooling system performance. And lastly, cooling unit power consumption to measure the electrical energy consumed by the cooling unit to evaluate energy efficiency and reduce unnecessary power consumption. Next, I will pass this presentation to my team member, Kairina Fahira, to explain methodology and demonstration.
Methodology of our IoT-based data-driven code source control system. First, we use Google Colab as our programming platform. The first section of the code imports the required Python libraries, such as pandas, request, JSON, and type. We also configure the ThinkSpot server URL and access token, which allow the Google Colab to communicate securely with the ThinkSpot cloud platform. Next, we move to the second session where the mount Google Drive and specify the dataset path. This path tells Google Colab where the dataset is stored so it can be accessed and processed. After that, the dataset is loaded into a pandas data frame. Our dataset contains four important parameters: inlet temperature, outlet temperature, ambient temperature, and cooling unit power consumption. We selected these parameters because they provide the key information needed to evaluate the cooling system. The inlet and outlet temperatures indicate the cooling performance. The ambient temperature represents the surrounding environmental condition that affects the cooling load, and the power consumption helps us evaluate the energy efficiency of the cooling unit. Okay, the next section of the code reads the dataset row by row. Each row is converted into JSON format and sent to ThinkSpot using HTTP post request. A 3-second delay is added between each transmission to simulate the real-time sensor readings. Now moving on to ThinkSpot. Here the transmitted data is displayed on a real-time dashboard. We use thermometer widgets to monitor the inlet and outlet temperatures and gauge widgets to display the ambient temperature and cooling unit power consumption. In addition, we configure the alarm rules in ThinkSpot. The system continuously compares the incoming data with predefined threshold values. If abnormal conditions occur, such as high inlet temperature or system overheat, the system automatically generates an alarm to alert the operator so that immediate action can be taken to prevent overheating.
Now, I will present the discussion of our project. Our IoT-based data-driven code source control system improve conventional cooling by replacing fixed setting with real-time monitoring. The system continuously monitor 4 key parameters: inlet temperature, outlet temperature, ambient temperature, and the cooling unit power consumption through the ThinkSpot platform. Based on our results, the cooling system operates an under average server workload of 65.21% while consuming only 0.76 kilowatt, showing a stable and efficient performance. From an engineering perspective, the outlet temperature increased from an average inlet temperature of 21.50 degrees Celsius to 26.49 degrees Celsius as it absorbed heat from the server. This demonstrates that the heat transfer process where higher server workload generate more heat and require greater cooling capacity. The system also improves safety through an automatic alarm such as high inlet temperature and system overheat, allowing operators to respond quickly before problem occurs. Most importantly, when the server workload decreased, cooling power was reduced from 0.83 kilowatts to 0.63 kilowatts, achieving about 24% energy savings while maintaining safe operating temperature. In the future, this system can be enhanced using artificial neural networks or model predictive control to predict thermal hotspot in advance and further improve energy efficiency. In conclusion, our project demonstrates that the IoT with engineering principle provide a smarter, safer, and more energy efficient solution for modern data center cooling.
Okay, next we go for the challenges and consideration. For the challenges faced in the system, we have 4, which is for the first challenge is the tropical weather problem, where the high outside temperature reaching up to 34.37 degrees Celsius, make it much harder for the cooling equipment to reject heat into the environment. The second challenge is rigid cooling settings, where the traditional cooling system run on fixed, non-adaptive settings, wasting a massive amount of energy when server workloads are low. The third challenge is the hidden threat of condensation. It is not just about the overheating, but if the gap between inlet temperature and the warm air gets too small, the water moisture can form on the high voltage hardware. And the last challenge is the data overload. Managing large volume of historical sensor reading over 3,400 data points requires an efficient coding to turn numbers into a useful action. So we move to the consideration. So firstly, we need to choose the right data path, where we need to select efficient HTTP and also JSON protocols, ensure that data flows smoothly from Google Colab to cloud without losing any data points. Human-centered interface, where designing the visual dashboard using colored gauge and thermometer instead of complex table, so the operators can make a fast decision during emergencies. For the third consideration is smart automation rules, where the programming the system rule engine to look beyond the simple upper limits, allowing it to catch a hidden physical risk like humidity and also system imbalance early. And lastly, for the cost and efficiency balance, we need to choose a low cost IoT upgrade for existing cooling, where the system, instead of replacing them with incredibly expensive liquid cooling setups. For the IoT system implementation, we use Google Colab as an agile Python programming environment to build the telemetry pipeline and handle incoming data, and then program the system to send telemetry data payloads like temperature and also power use directly to the cloud every 3 seconds. Instead of remaining rigid like traditional system, this setup continuously adjusts based on active workloads and tropical weather fluctuations. For the key features, we have three, which is the first one is monitored telemetry parameter stream, where Maslina had mentioned before about the system specification, which we have four parameters that we need to be looked on to, which is the first one is T inlet, T outlet, T ambient, and also cooling unit power consumption. And then for the next key features is unified HMI dashboard design. And the last one is automated alarm using rule engine, where system overheat will display as warning or critical status. Outlet temperature will display as critical status, and high inlet temperature will display as warning status. For the impact and result, first one is proven 245 energy saving, where the smart system will automatically slow down the air handling fans when server loads drop, cutting power from 0.83 kilowatts to 0.63 kilowatts. And then the second is fewer equipment failure, where the real-time dynamic adjust protect high voltage server machine from localized hotspot and dangerous moisture condensation. And the third one is a greener data center is 24% reduction help tackle a major global issue, as data center current consume roughly 3% of the world's total electricity. And the last one is better workplace environment, where keeping the cooling operation optimized the reduce excessive thermal stress and loud noise level for the operational staff. So for the conclusion, this project successfully connected Google Colab to ThinkSpot to turn raw cooling data into easy-to-read visual dashboard. By automatically adjusting to changing condition, the system proved it could cut cooling energy waste by 24%, which can significantly lower the carbon footprint of data center globally. So that's all from us. Thank you.